having trouble managing time and energy trying to fix a circuit board, not knowing what kind of calculations to perform, looking for a guide who will show you precisely what sort of calculations to go to when detecting trace resistance, if calculations are even that necessary. If so, that's why Captain Jack is here to help you find all information you need. When it comes to printed circuit boards, trace refers to the network of wiring, copper, insulation, and even fuses that make up the printed circuit board. In nearly all cases, if there is something faulty with almost any given electronic device, the chances are excellent that there are inconsistencies involving the PCB trace. Like the calculations of voltages, currents, the calculations of PCB traces also plays a very important role in every circuit board. If not calculated properly, it can consume a lot of our precious time to fix the board and possibly to rectify the board back to its original working state. It may also have to be designed from scratch, and no person, dead or alive, believe me, likes to redo such complex tasks. Okay, so let us understand more about the thickness of the traces. The thickness holds an enormous implication for a designer in the design process of the board. If it is ignored, the tracks may not conduct proper signals, which may lead to damage to the board. If the traces are not large enough to carry a certain amount of current, it may result in sparks and also damage the entire machine. So, how wide should the traces be? The answer is calculate the width such that double the estimated power could travel through them. Like, if a circuit is being designed for 1 watt, keep the traces such that 2 watt of power can easily pass through them. Did you know that watt is the unit of power and it was named after the scientist James Watt? If you didn't, I have told you now. So, depending upon the assumption, the trace can vary in size, anything between 30 mils to 200 mils for DC circuitry, and anything larger than that should be run through a power plane. Now, there is a formula for calculating the resistance of the tracks, which is as follows. It can be used in utter need or if the person is a procrastinator. Otherwise, simply the double power formula that we have discussed just now can be used. If you want to be extra sure of which tracks to be used, refer the treble table just shown here in this video for trace calculations. In that, the accurate relations are shown. Now there's these units that are used for calculations. I'll make clear the relations. First of all, the most common unit is the millimeter or mm. This unit is too large to be used for small tracks. So we have mil as the most common unit wherever the track widths and spacings are calculated or marked. The relation between mm and mil is as shown. 1 mil is 0.024 mm. Another unit which is used in Proteus is the thou, which is the abbreviation for thousandth of an inch. We can see the labels of racks in Proteus as T25, T30 and so on. Also there are units in Proteus which are marked such as 25th, 30th and so on in Proteus, which implies the same meaning. So now with the reference table shown in this video, you will be able to choose the appropriate tracks according to the signal power and other relevant factors. But what about the spacing? The circuits are very small and it is not easy to determine the spacing between the traces. So keep the spaces between the traces such that the space is at least 75% of the width of the trace that is being used, or keep it a common 6 to 30 mils, which depends on the amount of current flowing through the circuit. So that's all about the width, the spacing and the theory of turns or bends in the PCB traces. In the next video, we'll continue with the theory of electromagnetic interference, why to avoid the 90-degree bends, difference between shielding and grounding, and much more theory about the PCB traces. So mates, stay tuned with Captain Jack.